Hello, this is James Keene at Binary Mechanics Lab. Welcome. As you may know, Binary Mechanics Lab has been the winner in all major events concerning physics research excellence. All of these events, the winner. Perhaps the most important one is the century-long Physics Grand Championship race. As a result, a growing number of students are studying binary mechanics. It may help these students to look at what physics was like 25 years ago, in the previous century. We can see what physics was like in the last century, about 25 years ago, by going to CERN today, much as an anthropologist might visit a less developed tribe to document their progress. Here at this URL, we have accelerating science listed, and since CERN groups have not won even a single of the research in physics events listed previously, this might better say decelerating science. They have a 7,000-ton detector probing for fundamental particles. Apparently, they haven't got the memo as to what the fundamental particles are. We'll come back to that later. They have more than 3,000 scientists from 174 institutes in 38 countries working on the Atlas experiment. Now, what are all of these people doing? Because the research objectives that are listed, if you look at other documents, are very vague indeed. They want to do more search, I guess, for the Higgs boson, look into extra dimensions, wow, and particles that could make up dark matter, all very speculative, vague subjects. Now, if we motor over to the ALICE project at CERN, at this URL here, we see that they think that ALICE detects a quark-gluon plasma. Right here, this phrase has some big problems. Let's take a look at that. The next two figures are discussed in more detail in the paper titled Elementary Particle Energies. Briefly, what we have here are energy quanta associated with protons and those associated with electrons, their distance, plotted over a range from zero quanta density, which would be absolute vacuum in binary mechanics, up to 100%. That is, each quanta locus, which is a size L cubed, where L is the binary mechanic length constant, can only contain a maximum of one energy quanta. So if they're all filled, we have maximum energy density, which, by the way, is a completely new idea in physics, since back in the previous century, for example, the people at CERN, they think that you can have infinite energy density. In other words, infinities and singularities. Now, what concerns us today is this attempt to parse the energy density range here into subsections. You notice the plasma subsection, in conventional physics, by the way, is thought to represent the ionization of atoms. That is, the nuclei are separated from their electron shells and forming a plasma. Here we have increasing proton-electron distance. So, when the ATLAS project refers to a quark-gluon plasma, it's in essence misnamed because really they're dealing with a quark-gluon soup. Now, we call it here a lepton-quark soup. Why? Let's look at the next illustration, where we're going to plot over the same energy density range the proportion of total energy for different particle types. The blue is the left-handed electron, and then the right-handed electron would be the positron. These two curves here, the purple and blue, show that up here in this high energy density range, they predominate and they are leptons, while the right-handed matter d quarks, the yellow curve, and the left-handed d quarks, which are antimatter quarks, actually show less occurrence in this range above about 0.75 of maximum energy density. Therefore, we label this a lepton quark soup. So you can see that the naming and the whole conception of what they're doing in the Alice project seems to be a little bit misguided. Let me direct your attention to this statement here in the brief Alice project description. Protons and neutrons are in turn made of quarks bound together by other particles called gluons. Here we have a major problem. While the definition of binary mechanical space has been discussed in great detail elsewhere, at present our concern is whether or not there are gluon particles at all, whether they even exist. So let's just look at briefly how we parsed the complex amplitude in classical quantum theory in its wave function and took the absolute values of x and the absolute value of y, limited them to 0 or 1 to quantize energy. And so with the x and the y, we've got two kinds of bits which we're going to call the m bit and the l bit, which can only have values of 0 or 1. 0 or 1. Now, if we combine this spatial object, the spot unit, into groups of three along the x, y, and z axes, we define a spot. There are three one-bit binary variables involved in this parsing of the complex amplitude, which lead to the definition of 8 types of spot. The yellow is the electron, and we have the dark red, green, and blue as d quarks, and the antimatter d quarks are the light red, green, and blue, and the positron is shown in another perspective here, if we just look at the other side of the spot cube. Now notice we have our quarks, we have our leptons, the yellow and the gray here. Where are the gluons? At best, the L-type bits, which may be in some cases magnetic monopoles, are the gluons, but they're not separate kinds of particles defined here. There are no gluons. They don't exist.